Doctor, okay?
Okay.
Okay. Assalamualaikum and good morning, everyone. Thank you for joining us. So we are here today for a seminar on Taguchi method, design of experiment and process optimization. Our speaker today is Dr. Fatah. He's from Western Digital. Is that correct?
Okay. Sorry. Okay. Assalamualaikum.
Yes, salam.
Hmm.
Okay, Doctor, you can start.
Can start eh?
Okay.
Okay. Wait. Forgot to present. Entire screen. Okay. Okay. Assalamualaikum. Very good morning. So our online seminar today is about Taguchi method for design of experiment process optimization. Okay, first of all, start with my a brief about myself. My name is Muhammad Abdul Fattah. I'm a mechanical engineer, lecturer, researcher, trainer. About 5 years in industry experience and about 10 years in academic experience. I involved in research, innovation, product development with industries, communities, schools, and universities. Also have a wide vast experience in automotive manufacturing, quality QA and QC, robotics and automations, a bit about the C++, neural network for machine learning using the neural network optimization, and so on so on. So education wise, I did my Bachelor of Mechanical Engineering Automotive in UTM, Master in UPM, and PhD in Science USM. And my experience start with JVC manufacturing as a part quality engineer, and then as a technical executive in Sirim Berhad is a national precision tooling, is a subsidiary of Sirim Berhad, and about 10 years in the RBICOM universities, and currently just will join Western Digital in on 15 November.
Okay.
Okay, so this is topic that I will present or share today about the design of experiment, a little bit case study of a design experiment. If you guys have a Minitab software, is better, or I can give you a few minutes to install the software, the Minitab, and the Taguchi method. And lastly, we will apply the basic Taguchi method using the Minitab. Okay, so can I start?
Okay.
Okay, so everybody ready? So, what is the design of experiment? So, DOE is quite new for me. So, I've started using DOE in my PhD. So, it is a optimization method that used to optimize concept of robustness once the simulation method is available. And Taguchi method use the design experiment theory, which simplifies full factorial experiment into fractional factorial or orthogonal array study. So in my case, I will use factorial, and orthogonal array. So, where does it apply? Usually wide for solving optimization problem in various engineering fields. So DOE provides structural, well-designed, efficient approach to control the process. So if you have a large number of variables and you want to control the process easily or in a efficient approach, so this method is can be used, is reliable and quite easy to understand. Is a common approach. Full factorial and Taguchi are common approach that apply the DOE theory. So in addition, the Taguchi robustness method condense the full factorial experiment into a fractional or orthogonal array configuration. The experiment less time consuming, acceptable for most industrial conditions because of the orthogonal experiment for uniformity, decentralization, orderliness, and contrast. So this I will explain more in the case study and during using the software. So if you have time now, find the mini tab and install the trial version first. So what is a DOE? So it's a collection of statistical techniques provide systematic way to sample design space. So we will use the statistical way to sample the design of our experiment. And then useful when tackling new problem in which you know very little about design space. So when the studies is new for you, so using DOE is can simplify your method lah, and study effect of multiple input variables on one or more output parameters. So you have more parameters, but you don't know how to control the process of factors, so you can use this. Because I experienced my friend doing PhD like me, so I explained that he don't know how to design his experiment because the PhD is quite new for us. So how to design the experiment? So when I start using this, it's quite easy for me to plan my experiment and what is the level, the bottom level, the medium level or upper level of my experiment or process. So often used before setting up formal optimization problem to identify key level among potential design variables and identify appropriate design variable range, identify achievable objective function values. So actually we have the hypothesis before we come up with the results out, but somehow if the result is too much or too many, so it's difficult for us to conclude or analyze the process. So DOE is uh, quite good for me for us to use in context of robust design. Okay, and our discussion is to explore the design space. So continue. So factors and variables. So design variable is a factors. So we have certain variables or factors that we want to studies, and then we have values or design variables, which is level. So level mean none means bottom level, and then is a first level, second level, third level. So most of the time, the third level is the highest. The bottom level is the worst. So somehow we want to differentiate between uh, zero or none factors is a normal condition or actual condition of the experiment, and when you add something, so there is the start of the levels. Noise factor is variable over which we have no control. Example is manufacturing variation in blade thickness. So in the manufacturing, we assume that all the parts or components is produced uh, equally or same. The dimension is quite same, or we have the tolerance, but somehow there is a tolerance or allowance that allowed in the manufacturing, as long it's not out of the dimension. And then control factors equal to the variables we can control. Example is the nominal plate thickness. So output equal to the observation, yeah, or the objective function. So you have a factors, you have the level that you want to control that I mentioned before, the lower level, starting level, maybe medium level or upper level. And then you can come to the conclusion or the observation or analysis. All right. So metric experiment. So each row of metric corresponding to one experiment. So each column of metric corresponding to one factor. So each experiment corresponding to different combination of factors levels and provides one observation. So we have factor A and factor B, and then we have observation. Okay, this is a four experiment will be done for this kind of design. So yeah. So here we have two factors, each of which can take two levels. Okay. So this for A1, A with B1. So A1 with B2. And then change A2 with B1, A2 with B2. So we can come up with the observation of N1, N2, N3, N4. Okay. Okay. So this is for the nine experiment. So two factors or three level each. Okay, so we specify the levels for each factors, and then we evaluate outputs at every combination of values. Is complete but expensive. But so we have n factors, L levels, then we come up with the L and observation. So as we can see here, we have nine experiment. So nine combination of experiment. So start from A1, B1, A1, B2, A1, B3. Then change to A2, B1, A2, B2, A2, B3, and so on, so forth. So fractional factorial experiment. So due to combinatory explosion, you cannot easily perform full factorial experiment. So instead, consider just some possible combination. So what is the question to be answered? How many experiment do I need? So this is the question that you need to answer before you do any design of experiment. And which combination of level should I choose? So these two questions you need to answer when you do your optimization in your experiment. So need to balance experiment cost with design space coverage. So this is the fractional factory design. So initially, we may be useful to look at large number of factors superficially rather than small number of factors in detail. Okay, DOE techniques overview. So uh, first technique is the full factorial design. So the comment is the evaluate all possible design, and its expense L grows exponentially with a number of factors. The second one is the orthogonal arrays. Don't always seems to works interaction but moderate depends on which array. One at a time, order of factors. Latin hypercubics not reproducible. Poor coverage age division are large, and parameter studies capture no interaction. So in my case, I will use alternate race. So this is the parameter studies for specific. First, specify levels for each factor. Change one factor at all time, all others at base level, and consider each factor at every level. So as you can see, we have three A B. We have four factors A B C D, and then for each factors we have three level. For factors, three level each. So we have nine experiment. Okay. So when you do your experiment, you have several factors you want to consider or you want to control, and then based on this factor, you can choose which is the best of this nine combination of experiment, and it will show you the best combination with the best with the desirable result lah, or output. Okay, so this is orthogonal arrays. Okay, okay. We have here is four experiment, three factors, two levels. So this is the first four experiment. The combination start from A1, B1, C1, A2, B2, C2, A2, B1, C2, A2, B2, C1. Okay, this is if we have two levels. Means if we have lower and upper of our experiment. So this is if we have three levels, four factors. Mostly the experiment that have many factors like the missioning, optimization, got many factors also. This quite difficult if you have so many factors to observe. So this method can easily manage or arrange your factors and labels to control your parameters for your experiment. Okay, so design experiment. If you don't understand me in the first few slide, so you can follow this step. First, define your problem. Okay, after you define your problem, you get your problem statement, and then you can come up with the experimental objectives. Okay, so when you get your objective, select factors that influence the quality. Okay, you will select few factors, which is the best factor that influence or your product or output qualities. Then select control and next factor. Select levels for factors. Select orthogonal arrays. Select interactions and conduct tests. Okay. Finally, you analyze the result. Okay. I think we have a rest first because this start from Ken, Mr. Zul.
Yes.
Can
Yes.
we take a rest first?
Yeah. Yeah. Sure.
So if you have the time to install the Minitab 19 or for the practical after this,
All right.
you can try because actually for online training like this or online seminar like this is quite difficult for me to teach the Minitab lah. Before this, I usually teach my friend offline, easily
Yeah.
can share.
Oh,
So maybe we can take a rest for 10 minutes, and maybe you guys can install the Minitab first. Let's try fishing. If you want me to stop during the coaching or training, you can stop me. Okay,
okay. Okay, Doctor.
next we can continue at 10.
All right.
Okay, Mr. Zul, rest first. Okay,
Yeah.
right, you can go to Google, find Minitab, Minitab statistical software, try Minitab free for 30 days, and download. Okay, got many products here. Real-time SPC, statistical software, solution, resource, service. So, okay. So this is how it looks. Mm, maybe I can show you how I do my project. Okay, this is how it looks. Taguchi design, and Taguchi analysis, the ANOVA, source in ratio. Okay, the result. It's fine. Okay. Alright, we continue. So, based on my project and study of discrete model simulation optimization of different type nano-reinforced of the field using Taguchi analysis. So this is the optimization flowchart. Okay. So based on your problem statement, you can come up with the control factors and labels to study the quality characteristic. So from DOE, design of this experiment, I use a factor assignment, and orthogonal array. So from the experiment result, I get the response and signal ratio. Then I analyze the data. So for single response optimization, I use a Taguchi. So for today, seminar, I focus only in a single response optimization. Because if you want to focus for multiple response optimization, we'll be using GRE. So GRE is a different methods. It's quite long to explain in the work in a few hours seminar. Okay, so this is how the project of my optimization. So a little bit about my experiment. So it's a 16 experiment are required to study the entire flow soldering parameter space. So I assume you guys can use this type of experiment to understand how the Taguchi method is used. So I have a four level of nano reinforced solidation factor. The first level is a zero weightage percentage. Second level is 0.01. The third is 0.05. Fourth is 0.15. As for the uh, second factors, I use the material. So first is none, which means zero. No non-material added. First is TiO2. Second is nickel oxide. The third is a ferrum oxide. So these are my 16 experiment using the L16. Four level, two factors untuk kena array. And it has a 2 degree of freedom. Can handle four level of process parameters. So this is how you come up with the design of experiment for your study or for your experiment. Know your factors that you want to control first, and then know your which levels, and then you need to arrange the level based on your understanding or based on the literature review that you study. If not, if the arrangement of the level is confusing or not proper, you cannot get the good result. Okay, you need to identify which is level 1, level 2, level 3, or level 4. Normally we use level 1 is a lower, yeah. So,
Dr. Ta,
yeah, yeah.
what's the degree of freedom?
Degree of freedom is means two factors in this case.
Okay.
Means two parameters that you want to control.
Hmm.
Hmm.
Okay, okay.
Okay. Okay, in my case, I need to change the factors to A and B because Minitab cannot understand words. They can only understand A and B. This one is I edit after I do the somehow is a software to understand. So you need to put first you need to put weighted percentage A, material is B. uh, I'm lucky that after I change this, the after I get the result, then I change the so that I can easily understand. But in the first time I do it, I need to use A and B like this one. Correlation method. Okay, same. Already change. Kat boleh tadi. Because the software can only understand A and B. They don't understand the weighted percentage or material. So this is for our reference only. Okay, design. So Taguchi array L16, four level, two factors. So means that you have two factors that you want to control in your experiment, and you have a 16 combination or 16 runs or 16 experiment that you can sort out. You have many data, but all the data, if one combination you take five datas, so you need to collect or assemble all the data in based on this combination. So what are the combination? So these are the combination lah. So you have a 16 run. Okay, you have A is a weighted percentage, B is a nanoparticle materials. So the software understand A is one is level 1, 2 is level 2, 3 is level 3, 4 is level 4. For B, it understand one is a non, two is a TiO2, three is a nuclear oxide, four is a ferrous oxide. Because the software cannot understand what is your parameter about. It can only understand numbers. Okay, so this is uh, Taguchi L16 alternate array design matrix for my study. So you need to come up with your own study of this alternate array design matrix. Okay, okay, okay. So analysis of the scenario ratio, simple analysis or ANOVA. So the main factor of factor and the optimum condition on desired quality characteristic were determined based on the response table. Okay, when you want to study which factor or which condition is the optimum, so you need to determine based on the response table. Okay, the percentage contribution of the individual parameter cannot be determined using the simple analysis, but can be achieved through ANOVA. Okay, you don't know which is the best, so we can use ANOVA. ANOVA is analysis of variance. Uh, which one? This one. Yeah. Okay, ni. Okay. Let's go ke mana? Taguchi analysis saya. Yes. ANOVA ni analysis of variance. Okay, macam mana nak baca result, how you want to interpret the result, I explain later. So in this case, you can know that weighted percentage factors is better than material. Okay, but material still can be considered as a main contribution for your factors, for your experiment. Okay, so the percentage contribution of individual parameters P is defined as the pure sum of the squared deviation of each factor divided by the total sum of the squared deviation. So using ANOVA, you can use to evaluate the importance of recall parameters on the responder. So you have several factors. So how to rank the factors? So you can use the ANOVA. But after you get the result, you need to rearrange or assemble all the data based on the 16 run or experiment that I show you just now. So you need to come up with your the orthogonal array design matrix first. So all the data, if you have based on 16 design matrix, you have maybe 100, 200 or 300, you need to make it or using the mean or average. I use the mean or average for this method. For Taguchi analysis, you cannot use all the data. If you want to consider all the data using machine learning, neural network, other machine learning methods, because machine learning can use many data, can use interpret all kind of data. But if you want to use this one, Taguchi method, compress all the data in the design matrix. So you need to get the average or mean of the data, and then you can use to evaluate the importance of your parameters based on ranking. Okay, a higher signal ratio indicates that the run sequence perform better. So higher signal ratio perform better. Okay, the signal ratio can be considered of the optimization for single quality characteristic. Single only, not multiple. So kalau nak multiple, if multiple we need to use other method lah. So basically Taguchi method ni, if you couple with GRA, gray relation analysis, you can get multiple problem of the multiple quality characteristic optimization. So Taguchi only consider one quality characteristic only. Wait. Yeah. Okay. So this is the result of ANOVA. So how to interpret the uh, ANOVA for signal ratio? So refer to my experiment. I have two factors. First is a weighted percentage. Second is a material. So to optimize the quality of a solder joint reliability, the solder fillet hardness, I have three quality characteristic. First is solder fillet height, second is hardness, third is Young modulus. Okay, so based on these three, so I can get the signal ratio. So the ANOVA for signal ratio according to Taguchi orthogonal array, 16 different nano-reinforced solder experiment solution run were prepared for the optimization of solder joint mechanical properties, which is weighted percentage is the factor with the higher F value. So the first factor that perform better is weighted percentage, and then the second one is the material, because the A value for weighted percentage is higher than material. And robust design result in L16 was chosen with 16 analytical solution run to test the effect of each of the four factors on solder fillet height and the average effect is response for simulation. So what is the control parameters, the characteristic or the characteristic of the best itu factors. So F value of more than 4 indicates that the control factor have strong impact on the response. If below 4, so not strong impact. Okay, let's say you have a source of 4 control factors. Okay, you only have 2 that higher than 4. So that 2 is perform better in terms of process control rather than the other 2. So if you have many control factor, you can use this ANOVA for signal ratio to sort out all the uh, factors that not really impact or not really affect your experiment. And then the second one is the p value lower than 0.05 indicates that is significant to respond. So it's easy for us to understand because if the p value is lower than 0.05, like this one, the material is 0.015. So it's still lower than 0.05. So material is significantly affect the response. But the better one is the most factor that affect the quality characteristic is weighted percentage. So in my study, I consider both. Weighted percentage is considered and material is considered. So other factors I just sort out or just remove because not really affect the experiment. Okay, so this orthogonal array is total so that you can understand. So this is the result. So the Taguchi, when you come up with the so you just come up with the result. So you can show that label is missing. Sekejap. Yeah, missing label. So this is none. TiO2, nickel oxide, okay, ferrum oxide. So this is not a scatter chart or a trend line of graph. Yeah, this is the effect plot for mean and signal ratio. Means that you can understand your experiment based on two factors. Based on my two factors. The first one is a weighted percentage. So which weighted percentage affect the fillet heights most? So the first one is a 0.05, which I can easily understand that 0.05 weighted percentage is better than 0.15 and 0.01. In terms of material, for fillet height, nickel oxide is the highest, produce the highest fillet height compared to the ferrum oxide, because ferrum oxide is lower than 9. But lower is, in my experiment, still managed to fulfill the requirement of SSC, so the fillet height lah. So this is the if main effect plots for mean data or average data means. So based on this signal ratio and data means, I can conclude where my experiment or result of the fillet height. The first fillet height is my quality characteristic. So in this case, I choose larger the better, because we can choose a larger the better, nominal the better, average the better. So there's a few type of analysis that can be selected. Since the highest of the fillet height is always desirable, so I choose larger the better. And then the term signal in signal ratio stand for desired mean value for the response, and phase noise denote the undesired standard deviation value. So I come up with the response of fillet height, signal ratio, and mean. So I can easily rank which is the best. So in this case of quality characteristic for fillet height, material show perform better than weighted percentage. And then I can easily find the factors of 0.05 is better, and then nickel oxide is perform better. It's the most highest data lah for this kind of quality characteristic. And then we can easily get the optimal parameter setting corresponding for solid fillet height response is A3B3. So how to get the this one? Nickel oxide is the highest. 0.05 weighted percentage is the highest. That is our optimum parameter setting. Because I choose larger the better type of analysis. Why? Because solder fillet height is always this means for solder fillet height, if highest is better lah, but not really high because it has on its own. If too high, it can defect. But in this case, all the solder fillet is below the defect area, below the upper label, still can control. But in my case, I want to get a height, the better height of the solid fillet lah. Then understand, I think you can understand. So other response is the response of hardness, signal ratio, and mean. So for the larger the better type of analysis was selected for highest hardness. Of course, we want the highest hardness for the solid fillet. Then in this signal ratio, main effect for signal ratio, the weighted percentage 0.15 is the best lah, the highest. And if we refer to if you can see the Minitab cannot understand terms or words. It's can only understand numbers. So need to label this one label missing. So this 0 is none, 1 is TiO2, 2 is a nickel oxide, 3 is ferrum oxide. So I come up with the optimal design parameters. Same with the this one is missing. Modulus yang the modulus yang hardness. This one for modulus yang. So still the mechanical properties. This is all the data. So this is experimental result, and this is the signal ratio, signal noise ratio. And this is the result. And from the result, we can come up with the optimal parameter setting. Shows that for response of mechanical properties for hardness and modulus yang achieve its highest at A3B3. Okay. So I think that's all for the case study. Okay, Mr. Zul.
Yes.
You want me to continue with the software or you want to rest?
I think we can continue.
Continue.
Yeah.
But if continue, I go until finish lah. Until
Oh,
complete.
yeah, I think okay. It's okay.
It's okay eh?
Continue.
I think just finish lah.
Yes.
Alright. So this is a somehow a guideline for you. If you want to understand how to use the Minitab software or how to use the Taguchi method by using a Minitab software, this is the guideline, the simplest guideline for you to understand. So for this case study, Taguchi design experiment method was used in the project to evaluate the relative contribution of cooling channel design toward the hot stamping tool. So the main effects in the ratio, SN ratio, and analysis of ANOVA were employed to investigate the result and optimal parameters of cooling channel. So in this study, the factors that contribute to the hot stamping tools are cooling channel, pitch, distant cooling channel, and pitch between cooling channel and distant cooling channel. So for if you study the machining or hot stamping or any machining punya experiment, so you need to consider a lot of parameters. You need to how to control the process. So Taguchi can help you to understand or manage the design of experiment. Okay, so table one, factor and label description. Okay, diameter of channel 6, 8, 6, 8, 10, 8, 12, 12, 10. So three level. So three level, three factors. Okay. So first open the mini tab. Open. So analyze Taguchi design. Okay. So I don't want to disturb my experimental result. Uh, it's quite challenging to understand and get the best result. Even though it's look like quite simple, but to get the best result is quite challenging. I come up with many times of testing or trial before come up with before get the best result. Kita ni tak payah kacau kita dulu. New or new project. Okay. Okay, tadi bagi data 6, 8, 6, 8, 10. Kita copy je. Copy. Um, 6, 8, 10, 8. 10. Okey. 12, 12, 10. 12, 12, 10. Okey. So, okay. Oh, kena buat ni dulu pula. So, DOE Taguchi create Taguchi design. Okay, first remove flow. File. Start and DOE. DOE Taguchi create Taguchi design. Okay. Okay, create Taguchi design. So, 3 level design. Number of factor 3. So, 3 level design, number of factor 3. Okay. If you can follow me, if you not understand, I can help you. I'm not an expert, but I can at least can help you to understand. So, to level 3. Okay. And then L9. Then, okay. Okay. Oh, just, okay, remember. 3, label design, L2, L9. Code L tadi 9 column 3. This one L9 level 3. Level 3. Okay. 3 level L9. design L9. Okay, so vectors ABC, diameter, pitch, distance, diameter. I think you can follow me if you're interested. But to better understand, you need to follow so I can help you. Diameter, pitch, distance. It's more to practical so that you can understand easily what I'm doing. So label value 6, 8, 12, 8, 10, 12, 6, 8, 10, 6, 6, 8. So need space between the numbers 8, 10, 12, 8, 12 meter, 6, 8, 10, 6, 8, 10. Volume level B. Okay. So okay. Alright. So L9. So as you can see, Minitab will make your the combination for L9 for you. Okay. Store design worksheet. Okay. So you can easily okay. Taguchi array L9. Three factor, three level, three factors. So then right. So this is your Taguchi designer. Okay. So average main effect and analysis of signal ratio. Okay. So we have data here. So this is the result of three combination factors. So summarize result from so we need to copy the result. VMS VMS Jom boleh copy ni. Okay, so copy again. Masukkan dekat ni. Masukkan kat sini. Right, key in the result here. So this is the BMS. BMS. BMS MPE. So BMS MPE. Alright. Pick. Then go to DOE, Taguchi, analyze Taguchi design. Okay. Go to stat DOE, Taguchi, analyze Taguchi design. Nampak lupa pula. Oh, ada lupa step ni. Okay. Jadi masuk ni. Respon data are in. Okay, sekejap. Stat, DOE, Taguchi, define custom design. So factor ni, tiga ni, select. Okay. Lepas tu stat, DOE, Taguchi, analyze. Apa step ni? Oh, okay. Ni analyze. Bikin dia custom dulu. Stat. Ni dah. Data dah. Hash point. Tak keluar ni. Oh, okey, patutlah. 37 kurang 1 AM 3990. Oh, 3708. Okay, sampai Taguchi. Boleh. So respon data are in. Jadi kenapa tak boleh? Sebab because missing one data. So you need to complete all the data. Okay. So respon data are in VMS MPA. So graph. So select graph and then generate plot of our signal ratio for mean. Okay.
Betul tak sempat kopi GMS.
VMS tak sempat copy.
Ha.
Okay. Kalau saya hantar, sekejap. Ini. Saya ingat tak ada orang follow.
Ini dah.
Okay. Cik copy.
Okey, siap.
Siap.
Okey.
Okay. Okay, dah siap kan? Okay, semua data ni okay. Right. Stat, DOE, Taguchi, analyze Taguchi design. Then, respon data. Okay, ni, pergi ke sini. Select VMS or MPA. Okay, select. Then graph. So, just use signal to noise ratio, mean. So, ni display interaction plot matrix. So, kalau nak buat separated pun boleh. Each interaction on a separated graph. Okay. Apa lagi dia tanya? What else? Mesh to interaction analysis. Boleh select semua tapi nanti banyak sangat. dah tak. You can select all, but might confuse lah later. Okay, so yang ni signal to noise ratio, why smaller is better? Sebab dia nak lower value for BMS lah, promises low value untuk case eksperimen ni kena lower. That's why they select smaller is better. Dulu je lah, sekejap. Analysis sekejap. Okay, analysis. Okay, same. Term. Okay. Sekejap, term. Follow second. Term remain je. Just remain. Okay. Option. So smaller is better. This type of option, you need to understand your experiments first lah. Untuk eksperimen awak apa, which is the best? Paling tinggi bagus ke, nominal bagus ke, atau paling rendah bagus? So you need to understand your experiment and then select the best. So smaller is better for this case. Then okay. Storage ni sekejap. Setting storage single to noise ratio and min. Tambah semua boleh, tapi nanti your worksheet awak terlalu banyak. So click OK. Okay, boleh baca tak ni? So from here we can understand that okay, distance ni is rank number 1, pitch is rank number 2, diameter is rank number 3. So delta yang tinggi, higher delta will contribute to, will affect, macam lagi tinggi delta lagi bagus lah. Higher delta better result. Not better result, means the factor affect the respond better. So kan senang nak faham. Macam you have a many experiment kan, factor awak, lepas tu awak nak kena baca satu penat. Guna Taguchi senang, dia terus buat ranking. Kalau eksperimen yang banyak, lagi senang dia nak sort. They can sort out all the unwanted factors. So senang nak faham. Kalau kat sini, so main effect for means, kita nampak kat sini. So untuk diameter, okay, 12 paling tinggi. So untuk pitch, 8 paling tinggi. So untuk distance pula 6 paling tinggi. Dia akan menurun. So ni trend ni. So this trend easy for you to understand your experiment. So ni noise pula. Kadang-kadang noise sama macam mean, but boleh jadi juga noise different from ni. Kena tahu lah nature of your experiment. Okay. So ni result dia. So it can be observed that the parameters and the level of combination for minimum BMS is A1, B3 and C3. So boleh tahu. So dia buat ranking respon apa. So kat sini, so the lowest one is untuk A 6, untuk B 11, untuk C 10. So tengok result kita balik, jadi tak? Untuk diameter sama 6. Untuk pitch 12. Untuk distance 10. So kita punya Taguchi analysis ni berjaya, successful. Okay. Then analysis of simulation result. So compared to main effect, it shows that the optimum level for minimum VMS is N1B3C3. Give the similar optimum result for simulation analysis. Okay, so ANOVA. So why using ANOVA? So ANOVA mean the influence of cooling channel configuration to the strength of the hot stamp into. Okay, so guna ANOVA, ambil general linear model, ambil respon tadi. Okay, kita buat ANOVA. So macam like I said before, so ANOVA ni used to sort out, so to get the best, which is the best factor for your experiment lah. Based on the P value and F value, dia boleh come up with the ranking whether your factors is important or not. So sekejap okay, di sini okay, start ANOVA general linear model, fit linear model. Okay, so pergi ANOVA. So general linear model, so respond VMS NPA, so model ABC, random factor ABC. So respond VMS, okay, factor diameter, control, tekan control lah. You need to push click control, distance. Okay, select. Macam lain version baru. So covariate, patient. Okay. Okay, ada factor. Covariate dia ambil apa? So do a weight fit using weight in adjusted type 3 or sequential. So sum of squared dia ambil adjusted. Pairwise comparison, Turkey confidence interval 95 and test. Macam model option. Okay, adjusted two-sided 95. So memang confidence level of our interval is 95 is set. So need no transformation. Follow default, coding of factors ni follow default juga. Stepwise method. Okay, graph. Ini do a plot of histogram residual. Pakai pairwise comparison. Okay, regular sama. In addition, coefficient for covariate. Okay, in addition. So ini saja nak klik sebab nak nampak dia punya tu result. Simple table. Ni nanti semua keluar ni. Okay, just follow je dia punya um, default feed residual. Tak cuba feed sekejap, tengok dia ambil apa untuk storage. Tak ada. Ni plot. Okay. Kita okay. Alright. Factor coding -101 plus. So ni dia punya factor information. So ni dia punya ANOVA dia. So kita tahu kalau factor tu bawah 4, factor tu tak cukup kuat untuk support your experiment, can consider as your others parameter, but not good enough lah. And then should be the p value 0.05 bawah. So dalam case ni distance dia yang paling okay. Coefficient semua. So ni dia punya regression equation. Ni untuk dia punya residual, and then versus fit, then histogram, and versus order. So kita dah settle untuk general linear model ni. So general linear model ni dia come up dengan dia punya conclusion lah untuk eksperimen ni. So ni result dia sama macam tadi 6810028 P dia. Sama tak? Yeah, sama. Okay. So next is regression. So regression, pergi dekat stat regression and select regression. Okay, stat regression, select regression, fit regression model. So response same, mesh MPA, select untuk predictor ABC. Ini kena control, select control. So distance to diameter to distance. Okay, ABC. So residual for plot is a regular individual plot, normal plot of residual. Remain option. Ini juga coding pun sama, stepwise pun sama. Remain. So graph dia ambil tadi apa? Select normal plot of residual, normal probability plot of residual. So effect of plots. Okay, same result. Fit intercept, team table, so same, remain je. Terus display result. Ini kosong. Okay, storage, Okay. Kini result dia. Then select okay. So for regression, kita boleh dapat dia punya, we can get the regression equation for this experiment. Then coefficient, then model summary and ANOVA dia. So daripada ANOVA ni kita boleh nampak that vector mana yang paling bagus is a distance lah. Diameter still below 4, pitch above 4, but the most is distance lah. And pitch p-value dia okay, still below 0.05, and distance 0.002. So ni Pareto chart for the standardized effect. Ni nombor probability plot daripada ni kalau duduk dekat center kosong kan, so ni plus, so plus dekat belah sini, so yang ni yang mana less than 0 is over here. So we get the regulation analysis for VMS versus diameter, pitch and distance. So I think this kind of analysis is enough for you to understand your experiment. So that's all. Thanks. Okay. Okay, so that's all. So any question?
There's someone posting questions in the chat box.
Yeah. Chat box kena buka chat box. Sekejap mana sempat nak tengok chat box. Panjang. Okay, kena lah dia betul. Okay. I'm using version 19. In tab 19. This is the latest one lah. Yes, 19. Okay. Why p-value and generated model and regression is different? Okay. For general linear model, for regression, macam mana jawab it's different because of the different method different approach. It's actually Minitab is a statistical software. We have a lot of method, lot of version ataupun cara-cara untuk method to understand the data. So for general linear model, they use their approach. So that approach get different result. So for regression, you get different result. But it's based on you you nak guna yang which one you want to use, which one suit you, which one is better. If you want to use general model, you need to understand more, because general model ni dia banyak, dia ada beberapa lagi. Nak faham general model pun banyak, dia macam banyak version lagi. Memang ni kita ambil ni just fit general linear model. Dia ada pula mixed effect model lah. Lepas tu dia ada comparison factorial plot. So this one is different from regression. Regression for DOE pun different. So different different method is get different result. I cannot simply explain the whole because I not study that area. So I just study the Taguchi method, analyze and get the data using the signal ratio and main plot. That's all. I just find which is the best run for my experiment. In my case, I get out of 16 run, out of 16 run of experiment, the 14 is the best. For me, I can conclude I get my conclusion from the Taguchi method. So kalau nak jawab kenapa method ni result lain, kenapa method different method. It's a different method. You need to understand the nature of GLM. You need to understand language linear. For this, I study juga GLM ni. Quite long juga nak saya pakai regression analysis, GMM. So result pun beza. But actually dia punya equation pun beza. Regression equation pun different. So kalau yang ni simple sikit regression equation dia. P-value of course coefficient beza, ANOVA pun beza. So which one suit better for you to understand? Mine is Taguchi kan. Kalau macam ni tak cukup lagi. P-value pun berterabur, F-value pun semua bawah pada 4. So saya tak consider result ni. Saya tak guna. Okay. Question 9. Any other question? Tak ada?
Ada soalan?
Tak ada kot. Dia kalau dah start buat nanti baru ada soalan lah.
Ya, betul.
Sebab saya pun memang ambil masa lama untuk familiarize, untuk get the best result lah.
Sebab saya pada buat juga mini test, cuma saya buat setakat yang dapatkan ultimate parameters tu. So regression analysis semua ni still nak kena belajar lagi lah. Daripada belajar tadi.
Kita boleh pakai method yang banyak-banyak dalam mini test ni, tapi mana yang boleh guna untuk korang punya studies. Kalau ikutkan saya dah banyak versi dah ni, bukan satu versi, dua versi. Macam-macam saya test. AB lah, kadang jadi, kadang tak jadi. Normal lah. Tapi dia macam mana-mana software, bila kita dah biasa guna, kita nak explain kat orang susah. Tapi kalau offline, masa tengah buat tu dia macam trigger sendiri. Kalau nak explain kat orang susah. Kalau nak buat dalam bentuk slide macam dia akan jadi panjang. Ada benda yang kita ingat sendiri lah masa setting.
Betul.
So semua postgrad lagi dah
rasanya lah sebab yang ni pun kami share untuk semua student postgrad je.
Semua dah semua stage mana? Zul?
Baru first phase punya eksperimen dah dapat optimum parameter. So lepas ni nak run eksperimen lah, guna optimum parameter tu.
Cantik lah tu.
Banyak lagi lah.
Sebab mula-mula saya tak pakai Taguchi. So bila tak pakai ni kita shot sendiri kan. Macam kawan saya pun dia tak pakai kat, dia main belasah je. Bila main belasah ni kita buat ikut suka kita kan. Dia yang case kawan saya tu dia buat 10. Dia kata tak apa kita try lah 10. Punya 10 tu too much lah.
Dia buat full factorial ke apa?
Dia ikut suka sebab dia rasa oh tak apa kita buat 10 ni baru nampak graf tu nampak cantik sikit kan. But, bila saya dah tahu kenapa tak pakai Taguchi? Oh, okey. Dia try pakai Taguchi senang lah.
Satu lagi dia minimize the number of experiment kan.
Kalau guna step saya buat tadi, dia terus buang mana faktor ataupun yang tak okey tu dia buang terus.
Oh, okay.
Lepas tu orang pun senang nak faham. Macam panel pun macam okey dia tak banyak sangat komen tentang kita punya optimization tu, dia tak komen dah. Dia komen tentang lain dah. Sebab senang nak faham actually. Kalau tak macam mana kita nak tahu okey kita punya setup eksperimen ni ataupun design eksperimen kita ni dah okey belum. So tak tahu kan. Sebab lah kalau ada yang perlukan apa tu extra info, extra knowledge kan, PM je lah saya.
Okay.
Saya ada dalam grup apa tu Somek tu. Ada je dalam grup tu.
Oh, Somek yang ni post yang studentnya. Oh ya, sebab doktor baru grad
Ya lebih kurang lah. Tak payah panggil doktor.
Doktor dah tu.
Tu lah good luck semua.
Okay.
So kalau ada masalah saya akan bantu lah. Saya akan kata I'm happy to help.
Alright.
Sebab saya pun pernah berada kat situ. So bila kita jam ataupun kita dah tak tahu kat mana nak pergi cari kawan. So kawan bagi tips sikit. So cakap kat situ lah.
Okay.
Okay, so good luck, thank you for inviting me. Sorry lah kalau sebab saya memang agak busy sikit sekarang. Slide pun saya ambil je.
Okay. Thank you, Doktor.
Thank you. Good luck all. Thank you so much.
Alright.
Thank you, sir. Thank you, Doctor.
Thank you. Welcome.
Thank you, sir.
Kalau nak slide, if you want my slide, saya boleh share nantilah.
Boleh share dalam grup terus ke?
Saya share dalam grup.
Okay.
Okay, thank you.
Okay.